Hey everybody, in today's video, let's talk about how GANs, a class of generative machine learning models, right, generative adversarial networks, let's see how they've been used in material science. So I would say, broadly speaking, there's a couple of different categories in which we see them getting used. We see them for materials design, including for inverse design, one of these holy grails of material science. How can you make the exact material if you want some specific property? How do you know that it will give you that property? That's inverse design. And maybe we can start to do that with GANs. They use them for data augmentation. So how do you change your training data such that it is better representative of your final use case scenario by either adding or intelligently subtracting data? We can use GANs to generate data in a clever way. And then anomaly detection. And there's others, but those are some of the main ones. So let's just walk through a few papers where we see some of these in action. The first one is this organ GAN, which came from Guimaraes and company in 2017. And this is really used for generating new molecules. I think it was ideally for drug discovery. And the cool thing about this approach is that it combines GANs, which again generate new molecules, but they combine it with reinforcement learning, RL, where this allows you to now guide that generation process because you can penalize your GAN for making certain types of things, right? Maybe you made molecules that can't be synthesized, or maybe you made a molecule that wouldn't work as a drug, or maybe it's just not got the properties or whatever else, right? Your reinforcement learning, where you now have a reward structure that rewards or penalizes based off of compliance with these different attributes, allows you to guide the generation towards what you're looking for. So very cool approach. In this paper, they used a recurrent neural network architecture for the generator. They used a convolutional neural network for the discriminator. They trained this on about 5,000 compounds in the zinc database. These are drugs and non-drugs. And the types of objectives that they were after were things like solubility, synthesizability, and drug likeliness. Okay? So the next year, out comes MatGAN. MatGAN sort of built on the previous paper, this organ paper, and it did something. The main improvement that it did is that instead of using smile strings, it used a molecular graph as the input. So when you generate with molecules with graphs directly, there's some benefits. For one thing, by avoiding smiles, you can have a higher likelihood of generating a valid molecule output. Sometimes a smile string corresponds to a molecule that can't really exist, but graphs do a better job of making valid molecules at the outset. But they basically took the same approach. They still used reinforcement learning to steer this generation towards whatever their desired molecules were. And then this time they trained on a QM9 dataset as opposed to a specific one from the zinc dataset. Then we came to this clever paper. So this is CycleGAN. So this is in 2020 by Miziarka and company. And CycleGAN is essentially an extension of the very famous CycleGAN paper, 20,000 citations, right, in 2017, where if you're not familiar with CycleGAN, essentially what it did, it was an image-to-image model. So for example, if I provide an image of a zebra, we're trying to learn how to transform that zebra to a picture of a horse, or to go from a horse to a zebra, right? These transformations basically start with an image, and we want you to produce another image, but now where it's been transformed, so you have a variant of it. Well, they basically took the same idea here, where they're going to be trying to going back and forth between an input and an output using their generative model. So in this case, GANs are used to generate between these distributions, and then the discriminator is making sure that it's more or less matching what it ought to. So by providing, let's say, a drug that's good for a certain, medical application, they can make variations of it. And the hope is that by having similar structure and generating molecules that have similar structure, maybe they'll have similar properties, but they won't be the exact same. So maybe you can get around a patent, or you can get one that avoids a certain side effect, which is all really cool. So very slick approach, again, sort of leveraging the same idea of image to image. Okay, then there's this one, which I think is really interesting. It's MatGAN IP, which is like materials, generative adversarial networks in perovskites, I think that stands for, where again, it's still a GAN. This time it's specific to perovskites, but what they're trying to do is pretty clever. So the clever thing about here is they start with a generator that takes structured data, and then before just passing it directly to the discriminator to learn, real compounds from fake compounds, they append to it property data, which also can be real or fake. So the clever idea here is that as the model learns real structures and real property data, it learns fake ones and fake ones, such that as you generate fake data, maybe you could append to it real looking structured or property data. So this is actually a way to learn structure property relationships in this perovskite family, which I think is a really cool approach. So it's a way to basically learn properties as opposed to just generating new samples. You're trying to attach the correct property to them, which is pretty slick. There's cubic GAN. This is a tool that's been used to generate candidate structures in the cubic family. So they're specifically looking just in cubic materials. And so the type of information that gets encoded is, like coordinates, lengths, space group elements, but all in that cubic family. And then they basically say like, okay, now let's take white noise, pass it through our generator, where you're saying certain elements or certain space groups are the only ones allowed, but then random noise, and pass it out and see if it can generate new candidates. So they trained this off of things like the OQMD, which is DFT data, and they were able to rediscover most of the 300,000 or so cubic materials in that database. But then they were able to find a bunch that weren't in the database, and then they followed up with some DFT calculations, suggesting that some of these might actually be real materials. You'll notice here that they're using the Wasserstein distance. That's a different type of GAN discriminator at the end. We'll show you how that looks in a moment. And then you've got MatGAN, which is a cool paper. It's an interesting, it's an unusual representation. It's sort of like a one-hot encoding of the representation if you go back to our composition-based feature vector video. But instead of just encoding the value for each element in the formula, like 0 if there's no silicon, 0.5 if half the atoms are, silicon or aluminum or whatever, they actually have like 7 columns. So you've got as many rows as there are atoms that they want to consider, and then they've got like 7 columns. So if the stoichiometric ratio is like 7 of element silicon and 3 of oxygen, then they'd have a value in the 7th column for aluminum and 3 for oxygen. And that's a silly example because that compound doesn't exist. But that's how they went about encoding this, which was an unusual way. But what they did with this is they trained it off of a bunch of different data sets. They trained it on the ICSD, they trained it on Materials Project, they trained it on OQMD, and then they showed what happened if you then generated things after being trained on those things. And they generated lots of compounds. Like on the bottom left, you see, the training and versus their leave out. But then you see the blue data points are now when they start to generate, I think it was 50,000 data points versus 200,000. And essentially you see like there's a lot more space that could be out there to be explored. Now, my initial thought when I read this paper was like, but a bunch of those are going to be nonsense chemistries like noble gas oxides. But they passed those through SMACT. SMACT is a tool that came out of Imperial College London, Aaron Walsh and Davies, right? Where they check whether or not electroneutrality is probably maintained given that formula based off of what we know about common oxidation states. And they found that it's actually pretty good agreement. It matches pretty well the distributions from which it was trained, where the ICSD has really good electroneutrality compliance because it's based off of real materials. Materials Project and OQMD have less good compliance with it. And they're basically matching pretty closely all those distributions, which is a cool way to generate compounds. No structure, but it's a way to generate compositions. And then conditional GANs have been used to augment data and predict properties in other ways too. Like here's one used in high entropy alloys where, again, it's not just inputting a composition, they're inputting alongside the composition this conditioning where it's telling you the phase that's present. So in high entropy alloys, one of the big challenges is they're trying to figure out for a given composition, what would be the phase or phases that are present. And here they're encoding that, so making this a conditional GAN because they're providing this additional conditioning information. And they're using this to not only make predictions now for new materials, like what would be the conditioning for some new material, but also using this to augment their data sets, which they showed a slight improvement in their test performance when they did data augmentation. And then you've also seen lots of papers in the microstructure space. I'll just show this one from Sue and co-workers, where here they're using a Wasserstein GAN. Again, more on that coming in a moment on how that differs. But they take real 3-dimensional microstructure data, and then using their GAN, they're able to train off of that, and with their Wasserstein GAN, they're able to recreate fake versions of that data. So here on the top, for example, you see these are real 3D microstructures, and then on the bottom, you see these generated synthetic images from the WGAN. And what's really cool is they actually compared this to one of the state-of-the-art tools, Dream3D, which is a grain-based genetic algorithm approach. And they're showing that they actually do quite a bit better. And you can see that in these sort of histograms where the green comes from Dream3D, where it's not matching, things like the pore size, the phase amount of the nickel versus YSZ. But the blue and the pink, blue and the orange match pretty well. That's the original in the GAN. So pretty cool approach. And we see lots of papers in that space, which makes sense because GANs, again, came out of the image field. So it's not surprising that they're doing great in the image, including 3D images space. I am excited to tell you about some of the work that our group has done with GANs over the last 4 years. It's been a major area of research for my group, and some of this work finally got out and published nicely in the journal Digital Discovery. You can see the article here. It's called Generative Adversarial Networks and Diffusion Models in Material Discovery. So in this paper, we sort of compare and contrast the performance of GANs and diffusion models, which we'll cover in our next video, and how they relate to generating new crystal structures. And that's sort of a long-standing problem. I would say solid-state chemistry has lagged behind organic chemistry for a long time in this space because our organic chemistry friends were able to make an individual molecule. You saw MatGAN and organ and mol CycleGAN. Those were all making individual molecules. But when you then say I don't just want the molecule, I want to know how it packs to form a crystal structure, that's a much harder question, right? And so to do that, you have to have some sort of invertible representation that accounts for symmetry of the periodic lattice. And that was missing until just recently, just until 2022, 2 years ago. Our friends at MIT and the University of Singapore, as well as us at the University of Utah, sort of independently came up with an approach, and they both got published the same year. And in both cases, these were invertible crystallographic representations that allowed us to now do generative inverse design using generative models, essentially. So the one from MIT and company was FTCP. Ours is called Crystal-to-img, and they work in very similar ways. In both cases, you're taking the sieve information and you're going to put it into this representation. If you're not familiar with the sieve card, I'll show in a minute. But not to sort of bury the lead, the fact is that now these generative models with these different representations that are invertible are able to make these really convincing new structures. The ones you see on this slide actually come from the diffusion model, which is way outperforming any of our GANs. And you'll have to stay tuned in a couple videos. You'll see how diffusion works, but it's pretty effective. That said, when we started, we were working with GANs. And the GAN architecture looks like what you've seen me talking about, right? You've got real materials from some sort of crystal structure database. We were using the Pearson. We pass those into a discriminator, and we've got fake materials, fake sieve cards, essentially, coming out of our generator. You can choose to include an additional step here to toss out things that you think are going to be nonsense. So things that are far from the hole, you can do a quick machine learning prediction of how the distance looks from the convex hole, or if it doesn't pass the SMACT, calculation for electroneutrality, you can toss those things out because you think they're going to be unstable or unrealistic. And that makes this work a little bit better. It makes it more stable because in general, the discriminator has a much easier job than the generator. Other ways to get around this is people will use a smaller architecture, like fewer nodes, fewer layers for the discriminator, but a much beefier version for the generator, right? But these are options you have. So we started with a more or less what's called a vanilla GAN architecture. Now we need the information from the sieve card. So the sieve card's got things like our A, B, and our C, right? That's telling the unit cell dimensions. You've got your alpha, beta, gamma, which tells you the angles between those axes. You have to have the space group number because from that single value of space group number, it tells you all the different symmetry operations that take place. And then you have to have the basis, which tells you the type of atom and where it's located and its Wyckoff number, right? That's not a lot of information, right? And yet from that limited amount of info, you can produce these really good, periodic lattices for, defect-free, there's no dislocations accounted for here or defects or impurities, but it's at least a way to represent, crystal structures that are candidates, okay? And even better, there's lots of great tools like MatGAN that make it easy to extract this information. And there's databases where a lot of this stuff is stored. So we're using the Pearson database. It had 300,000 sieves, of which about half of those had both the space group and the basis. Turns out it's hard to solve for the basis, but it's pretty easy to get the space group. So still, 143,000, that's pretty good. That's going to be plenty to train on is what we figured. So now comes to our representation. And in the very early days, like way back during COVID, we came up with this. It was really simple. And technically, this matrix, it could have been a single row. It could have been a vector, right? All you need is ABC, right, for the dimension of the unit cell, alpha, beta, gamma for their distortion, space group for all the symmetry, and then as many additional columns as you want to represent unique atoms in the basis. Now, some of the atoms, compounds in our database had 200 different atoms, which is crazy. And some only had a single atom. So you have to make it flexible to accommodate for different numbers of atoms in the basis. I think we ended up having it allow up to 52 different atoms, which captured the vast majority of the compounds that we wanted to consider. Now, why did we average it over 7 times? It was just more stable. Again, one of the big problems with GANs, which is what we're starting with, is that they are unstable. And so averaging this value 7 times over turned out to make it much more stable. If you took the average A value, the average B value, That was pretty clever. And it also allowed us to encode additional information, like for each atom in the row, we could encode the fractional coordinates of where it's located on the ABC directions, or just the XYZ positions, which was convenient. Okay. Now we go to do this, and my students like, sweet, we got this to converge. I've got a sieve card, and we go to open it, and we get these errors, and we look into the error in Vesta, and it has something to do with the symmetry not being correct. And we look into it, it's like, oh, okay. The space group was over 195, meaning this is a cubic structure, and yet maybe the A was not equal to the B, was not equal to C. So we had to force it to obey some symmetry rules. We had to make sure that the angles were 90, the equal lattice parameters. So we just had to do some averaging. And we had to do that with all the different space groups to make sure that it was not violating symmetry rules. So with a little bit of work and a little bit of constraints that we introduced at the outset of our generator, we were able to do that. It didn't always need huge shifts to make these, by the way, happen, but they did require some nudging, some constraints. Okay, so we go through a bunch of other work, and then we get my grad student to try it again, and this time he gets it to converge, and we go to open it, and we get another error, and it's like, hey, I don't know what atomic number 22.145 is. It's like, oh, okay. Yeah, that doesn't make sense. So I initially told them, like, well, okay, just round it to the nearest atomic number. But the problem with that is, let's say you did that, well, then you might suggest that all these different compounds were present in your formula. But 100 years ago, almost to the day, right, Pauling pointed out in his fifth rule, parsimony, that things don't tend to have 20 or 52 different atoms in the formula. They tend to be single, binary, ternary, maybe quaternary. They don't tend to have a bunch of different elements in them. So the way that we got around that was through k-means clustering, where maybe it had 14 different elements, but we can force that down to a single one, or a binary, or a ternary, or quaternary version. So we made different versions of each, but all in reduced dimensionality in terms of the number of elements used. And when we did that, we finally got a sieve card that would open, and it was a disaster. This one on the bottom left was this is the first one I ever opened, and I was just like, you know, it was a clever idea for my student to try and do this, to try and generate new periodic crystal structures, but this was so bad that I really was like embarrassed to tell anybody about it. And so I was like, you know, good idea, but let's move on. Let's do something else. And he was, you know, credit to him. He's like, well, hold on. I think we can do better. Like, that was just the vanilla GAN architecture. There's so many different architectures. You can add normalization. You can add LSTM. You can do lots of different stuff. So he starts trying things, and he gets a few to converge. And if you look at them, they're still really bad. Like, if I compare this to sort of the progress that we've seen in generating faces, this looks way more like the very first face, which is not convincing anybody. And so these sort of the approach that we were using so far was just not going to cut it. So there's a couple problems with what he was doing. The first is that the traditional GAN uses a sigmoid function. I talked about this before. This is what it looks like. And CS people love the sigmoid, right? Because again, if your node comes down to a single value at the end, if your neural network comes down to a single node, then the value in that node is the X value. Or the value coming into that is the X value. You can represent the final value on that node as A, which is just this simple thing. It's basically either 0 or it's 1 for most values of X, and only between like -4 and 4 is there like much ambiguity. So that's a good discriminator, but it has this problem of the slope, and the slope is what we use in our loss function for backpropagation. That's approaching 0. So we're losing our slope. We're losing our ability to make big changes to the weights of the model to make it even better. The example I always give is like, if you're running a marathon, imagine as you got closer to mile 26.2 or whatever it is, you start moving slower and slower. I think that's what was happening here. As we were starting to generate compounds that looked kind of convincing, we just weren't getting as much actionable information to our generator and discriminator because of this choice of our activation function. Well, the good news is that there's lots of other different ones we can use. Like, for example, the Wasserstein GAN is a way better tool. Instead of taking this representation of your material, this matrix thing that I showed you, and flattening it down to a single value, what if you take that entire representation and you reframe it as a cumulative distribution function, right? This cumulative distribution function now can be compared to the distribution function for real materials. And when you're comparing distributions, there's all sorts of tools. There's like Kullback-Leibler divergence, or the Earth mover's distance, which tells you how much work it would take to make one distribution overlap and look like another. And the benefit of that one is that it has a linear output. So no matter what your model's spitting out, you get sort of realistic compounds. So this was now about a year-ish later from when we started, and I went to the fall MRS meeting, the big meeting in my field, and at that meeting, I was able to show a bunch of chemists this image, and I was like, 4 of these are real and 4 are fake. And if I showed them the chemistry, or if I showed them average bond distances, like all these things would give it away. But at least like a couple people in the room might have fallen for a few of these fake ones. Now, there's still problems. If you look at the ones there, there's some issues because there's atoms on top of each other. That's the main problem. If you looked at our representation, we learned the basis, we learned the unit cell size, but then we relied on the space group to go from the basis here on the left to the fully populated crystal structure where all the atomic positions are noted. And in doing that, you got atoms like on top of each other with crazy distances. It was really bad. And the only way around that was with a new representation. So we chose this representation with a direction graph, which allowed us to directly learn what are appropriate distances between the atoms in our basis. So you see all the different columns in this direction graph represent unique atoms in the basis, and all the different rows also represent those same unique atoms in the basis, right? And so doing that, we can learn what the appropriate directions are. And my student Sterling pointed out that he's like, oh, you know what? You could do like a Euclidean distance, like a pairwise distance, or you could do a unidimensional distance. Like what's the distance in the x direction versus y versus z? And in doing it that way, you're actually able to think about this as an image, right? You've got 3 channels. So he called this crystal-to-ping, right? If it's just unidirectional distance, or if it's pairwise direction, the Euclidean distance, then it would be grayscale. But if you break it into 3 dimensions, now it's like a color image. And that color image represents a material, which I think is really cool. Like that is a material and all of its periodic crystallinity, and it's an image, which is so great because once it's now as an image, that allows us to turn it loose on all sorts of generative models out there. Things like Imogen or DALL-E or Palette or Gemini or all these different ones that are out there. You can start to use it with them. So we call this crystal-to-ping, and there's a variation of it called crystal-tense, which is we're now using. Now there is a catch. If you're going to have a direction graph, it's easy to construct the direction graph if you know the XYZ positions. For example, from atom 1's perspective, I can learn where atoms 2, 3, and 4 are in the X direction, right? Atom 2, going from 1 to 2 is a distance S, but going from 1 to 3 in the X direction is 0. Going from 1 to 4 is a distance X. And you do the same thing for atom 2 and 3 and 4, and you create these direction matrices. And you could do that in the Y direction, and you could do that in the Z direction. But the problem is that our generative model is going to create a direction graph, and we are expected to deconvolute from that graph the XYZ positions, and there's some ambiguity. For example, if I'm using this direction graph that gets generated by our generative model, I'm going to say, great, from atom 1's perspective, I can locate atom 2, 3, and 4. But the problem is that from atom 2's perspective, I have to do the same thing. I can locate atom 1, 3, and 4. And from atom 3's perspective, I can find, 1, 2, and 4. And these don't all line up in the exact same spot. There's some ambiguity here. So my initial thought was to tell my student, well, just average it, take the average. And that's what we did. But he was clever and he said, let's hang on to the standard deviation. Like how much variability was there? Because our hunch is that models with lots of variability weren't exactly certain on where to put that atom. And models with lower variability might be better models because they were quite certain on where to put it. So when we did this, we were able to now produce the XYZ positions of all of our atoms and start to generate crystal structures using these different generative models. And since we're talking about GANs in this video, what we found is that the basic GAN was not very good. If you look at the variance in predicting lattice parameter, it was pretty big. It didn't know what lattice parameter to use. It had no idea what space group to use. Like this is the variance squared of space group, so it had no idea. But as you move towards Wasserstein GANs, it got way better. And when you got to diffusion models, which will again, 2 videos out, it was even better, right? So, and you can see it in the output, right? Here's our vanilla GANs. These are the types of structures. You can let it run and create as many as you want. But we noticed, first off, the unit cells were way too big. And the types of atoms that it was using were really pretty basic. It was the same ones over and over. That's not very good. Now, the Wasserstein GAN did better. There's more diversity of structures, more diversity of symmetries. There's more elements that are being used, but they're still pretty crazy. And then the diffusion models are doing really good. They're producing diverse, symmetrical crystal structures. There's still some serious problems with the chemistries that it's spitting out because we're not ever encoding chemistry. So it's producing things like barium, sodium, oxygen 4. Basic electron counting will tell you that doesn't work. So we're having to screen through these at the end using SMACT to toss out things that wouldn't be electroneutral. But we think that that's a solvable problem. We just haven't addressed it yet. What's really cool is you can look at the distribution matching of training data and generated data. So this is showing you the distribution of atomic numbers in the real distribution, that's the salmon colored lines, and then the generated data. And you see that on the far left in our vanilla GAN, it's mode collapse. It thinks everything is like a transition metal actinide, right? Whereas the Wasserstein GAN is using more of the periodic table, but it's not learning that things like oxygen were really present in the data set that we trained from, and so it's not really representing it well. Meanwhile, the diffusion model is learning to match this distribution really well. It knows that things like oxygen are more common and some of the things like noble gases are less common. The same thing in space group and lattice parameters and all the other metrics we looked at. They tend to see mode collapse with vanilla GANs, better coverage with Wasserstein, and really good matching with the diffusion model. Same thing if you were to take the generated outputs of these things and then predict their properties, things like predict the band gap or the modulus or Poisson's ratio, and compare that to the violin plots for real materials, we see that it tends to be pretty good matching for these generated materials for their diffusion models, but less good for the GANs and Wasserstein GANs. So that brings us kind of to this point where the generative models that we're at least using to generate new crystal structures, while they're not perfect, I think that they're approaching utility. They're sort of like at this point, like that face is not exactly perfect, but it's good enough for some stuff. I think the materials that we are generating these crystal structures, while they're not perfect, they're good enough for some stuff, which is pretty cool. Okay, in our next video, we're going to jump into how variational autoencoders work, and then we'll eventually see some examples of how those look in material science. And then we're going to move to diffusion models and show how those work with some examples in material science. Stay tuned.